Good, so everything appears to be working. So, like I said, today we're going to focus on structure drawing. I believe I've already made the point that drawing structures is pretty much the main way we communicate in the subject of organic chemistry. There's very little math. We might do a little bit of arithmetic today, by the way, but beyond that, as I think I've brought up this point before, if you can count to 4, you're in pretty good shape because carbon is 4 bonds. And if we can internalize that, that will get you through a surprising amount of the material.
I think I'll have
but as long as we're clear that carbon has 4 bonds, then we're in good shape. So last time we covered, I mean, we already touched on the idea of valence, I think, the idea that each type of atom has a certain number of bonds it likes to form, at least while retaining a formal charge of 0, which is every atom's favorite formal charge is 0. Certainly the non-metals at least. And so we talked about the idea that it's possible to some degree to draw structures like this by considering the number of valence electrons around each atom and observing that we need 2 electrons to make a covalent bond, and just making sure that everything gets paired up as appropriate. It makes sense, for instance, that oxygen likes to form 2 bonds because it has a valence of 2. It needs 2 more electrons to gain that all-important octet of electrons. And most atoms obey the octet rule. In other words, when they have a formal charge of 0, they should have 8 electrons around them. Most atoms, there are exceptions, hydrogen being by far the most common exception. When hydrogen's bonded to something else, it should have only 2 electrons around it, not 8. And so that's where we get these non-bonding electrons, these lone pair electrons. And so we already touched on all that. And this is a perfectly valid way to draw structures. If it works for you, fantastic. I'm not going to try in the slightest to talk you out of it. But we'll go over another way to draw structures in just a moment. But today I also want to cover the idea of not just drawing structures, but multiple different ways of drawing structures, just to at least get you guys started on that. It's okay, by the way, if you don't walk out of this class being big experts in structure drawing. You have to practice. That's maybe, if you remember only one point from today, one thing to take from this class, that I might have already said it, excuse me if I have, but you're not going to learn how to draw structures correctly merely by memorizing the ones I draw in class. That is not an adequate level of understanding. The successful student should be able to look at a structure that you've never seen before and understand it. Understand which atoms are bonded to which, check out all the valences, make sure everything's obeying the octet rule, pick out any non-zero formal charges, this type of thing. Just memorizing what we do in class is not enough. It's a start. I mean, I guess if my choices were that or nothing, I'll take it. It's a start. But you should aim to, I would say, in order to prepare for exams, one thing to take from this unit is being able to draw structures well. I usually say it's important in organic chemistry to be able to draw structures correctly and quickly. The reason I add quickly is because, as you can imagine, if it takes you 10 minutes to draw one structure, you're going to be in trouble on the exam, even though I'm not grading your structure drawing directly. But I think you can all see that intuitively. So that's what I would suggest you should be aiming for. We'll also bring up the ideas of electronegativity and both bond polarity and molecular polarity. These are things you'll get to practice in the OWL assignment, and they're things you've had in Gen Chem as well. But I figured it wouldn't do any harm for me to put some definitions down here just to make sure we're all on the same page. Here's how I would define these terms. But I think what I will start with is the idea of structure drawing. I kind of want to get back to ethanol here, or maybe at least propanol. But for now, I think I can get us into structure drawing. Now, in your class notes, I've left something that I intend to be helpful. I hope you find it helpful. I have kind of a summary. You'll see it in the part on formal charge, which I would like to get as far as formal charge today. And in that section of your class notes, I've put what you can expect to be true about the most common types of atoms when they have a 0 formal charge, and also when they have a +1 formal charge and a -1 formal charge. And I should say, I would say if you draw a structure and you wind up with a formal charge other than -1, 0 or +1, something's wrong. You've made a mistake somewhere. I think you'll find when we draw organic structures, I mean, I can't think of an example of an organic structure with an atom that has a formal charge other than +1, 0 or -1, with 0 being by far the most common. So certainly do your best to make sure, I mean, unless you go into it knowing you're going to have an ion, then you want to make sure that the structure reflects that. But certainly try your best to make atoms of a formal charge of 0 to the greatest extent possible. And then you will also have occasional formal charges of +1 or -1. But if you see something that I give you a formula for calculating formal charge also. It's not the only correct way to write it, but you would have covered that in Gen Chem as well. I'm seeing this question in chat, and of course I'm not supposed to answer questions in chat because the class isn't hybrid. So some of you might be wondering if there's a group me for this class. I do not know the answer to that question, but my experience is that students are always very resourceful in setting that sort of thing up. So they always invite me too. I'm like, you must be joking. I don't want to go anywhere near that. I don't want to know what people are saying about me. So just put it out there if anyone is interested in setting that up. I am sure, based on nothing in particular, but I'm sure that people would be interested in that. Good. So anyway, so where were we? We were talking about valence and how to draw structures. Oh, and I was talking about formal charge and to aim for structures for all atoms, preferably having a formal charge of 0, but occasional charges of +1 or -1 are fine. Other than that, outside of +1, -1, and 0, there's bound to be a mistake somewhere. I can't think of an exception off the top of my head. Good. So that being said, this is not the only correct way to draw structures. Another way you might have learned in Gen Chem is by counting all of the valence electrons. And I thought and sort of taking account for all of them. So let me think of something besides this one would be C2H5OH or C2H6O, which brings up the whole idea of isomers, which we need to get into today also. Let me think of another one. Let's steer clear of isomers for the moment. Let's do C2H5Br. Let's do that one. So the idea is to count up all of the valence electrons, disregarding the inner core electrons, which we discussed last time, and making sure that you account for all of the valence electrons exactly once. And if you do that, you should wind up with a correct structure. Usually you want to put, the rule of thumb is the least electronegative atoms will go in the center of the molecule. There are exceptions to that, but a lot of that also comes pretty easily once you understand the idea of valence. And you understand, for instance, the valence of hydrogen is 1. So you're not going to put a hydrogen at the middle of the molecule if it can form only one bond. And in fact, halogens also have a valence of 1, so that your halogens are, of course, fluorine, chlorine, bromine, iodine. They're the, yay, we have a periodic table. They would be this 7th column of the main group elements in the periodic table. So those also tend to form one bond. Are there exceptions? Yes, but the exceptions I think you'll find are going to be in inorganic compounds. I think in organic compounds, you're overwhelmingly likely, if not 100%, at least 99.9% likely to find every halogen will have exactly one bond. So that means we have to put the carbons at the center. That makes the most sense. And not only that, but we can't, got thicker all of a sudden. Maybe that's a good thing. Oops. That's actually not necessarily a bad thing. It'll make me draw a little bit, oh, I bet I know why. Okay, just making sure it's on the right setting. So we want to make sure to put the carbons at the center, and besides that, we know we'd better not put anything in between them. We can't put a hydrogen in between them, because then the hydrogen would have to have 2 bonds, which is impossible. Make sense so far? So we'll put the 2 carbons in the middle. It is still thicker. I don't exactly know why. And after that, we arrange the other atoms around these central atoms in some sort of pleasing geometric figure. Don't really have to worry about it too much unless you're also going for the correct molecular geometry, which is something you studied in Gen Chem. I know you went over the VSEPR model and you learned to tell whether there's really only 3 VSEPR shapes that we're going to be concerned with here, by the way. Linear, trigonal planar, and tetrahedral. Those are the only 3 templates, if you will, that you can build an atom on. There are only 3. So we're not ever going to get into square planar and square pyramidal, and we're not ever going to see those. Octahedral. Those, again, you find in inorganic molecules. So we'll put the 5 hydrogens and the bromine around these 2 carbons. And it doesn't really matter where, because I've very kindly picked an example where it won't matter. What about examples where it does matter? We'll get to that. That's the idea of isomers. We'll get to that. However, this compound doesn't exist in multiple isomers. And so once we've done that, it actually really is almost a little too thick. Once we've done that, well, that is once we've put the atoms around in some sort of relatively pleasing geometric shape. And again, you'll notice I could have put the bromine in any one of those 6 positions. It's the same thing. That's going to be, again, another key point from today, is learning to recognize, you'll get to practice this in OWL. None of this comes except by practice. So you have to practice, but that's okay. But it's being able to recognize whether 2 structures are identical, in other words, 2 different ways of drawing the same compound, or are they what we call isomers, structural isomers or constitutional isomers? And we'll talk about that today too. Good. So once you've done that, then we need to count the valence electrons in all of the atoms. And so each of the carbon atoms has 4. So 2 times 4 is 8. And then we add in from the hydrogen, each of the 5 hydrogens is 1 valence electron. So we add that. And bromine, like the other halogens, has 7 valence electrons. So we add that in. And unless I've lost my mind, we have a total of 20 electrons that we need to account for. And so the rule is we need to account for all 20, and we don't get any more than that. We need to use all 20 of those electrons exactly once. And so then after that, we'll simply put in bonds. Each bond will take 2 electrons. And so I think I just made 1, 2, 3, 4, 5, 6, 7 bonds. 7 times 2, since there's 2 electrons in a covalent bond, is 14. So 20 minus 14, there's 6 electrons left that we need to account for. And so next what we do is we make sure that all of the atoms that obey the octet rule have 8 electrons around them. We'll start with any of the peripheral atoms, and we'll do a couple other examples besides this, by the way. Starting with the peripheral atoms and ending with the central atom or central atoms. And then if any atoms still lack an octet, that's where multiple bonds come in. We'll do an example of that as well. So the thing that jumps out at me is all of the hydrogens are fine. Hydrogens only need 2 electrons, and each of the hydrogens has 2 electrons around it. 2 shared electrons in the covalent bond. Likewise, both of the carbons are fine. They both have 8 electrons around them. The atom that's missing electrons is the bromine, and we have 6 electrons left, and lo and behold, that's exactly how many we need for the halogen to obey the octet rule. So that's just one of any number of correct ways to draw that molecule. Again, the bromine could have gone anywhere. Sometimes when people ask me the question, we already discussed this, how the questions sometimes come across when they ask, if I put X, Y, and Z, will you take off points? But sometimes when people ask that question, the answer is interesting. And this is one of those times. So if it were that type of exam that weren't multiple choice, and you put the bromine in another place, would I take off points? The answer is not only would I not take off points, I wouldn't even notice. That tells you something. That's helpful information. It means that when I look at it, I just see it as being the same thing and I move on. And so that's what I would suggest you guys aim for, is getting to the point where, at least after some inspection, it's okay if you don't know instantly. You know, it takes practice. You're not born knowing this. But that's what you guys should aim for, getting to the point where you can recognize whether 2 structures, even if you've never seen them before, are identical or of different compounds. And we'll talk about that. I still want to talk a little about isomers today, which we will do, just keeping an eye on the time. Good, let's do another one. Let's do one with multiple bonds. Let's do formaldehyde, CH2O. And if it were necessary for me to give a little hint, I'll give a little hint on this one. There are no OH bonds in formaldehyde. And even if I didn't give that hint, I think you'd very quickly find out it's not possible. There's no way to do it and have everything obey the octet rule. So there's no OH bonds. So again, the least electronegative atom usually goes in the middle. In this case, it's carbon. And carbon is the central atom here. That means in some sense, we have to have the oxygen and the hydrogens around that carbon in some sort of pleasing geometric shape. And actually, although I see I've kind of instinctively set up the molecule to be trigonal planar in shape, which in fact is the correct shape. And we'll go over how you can know that too. I'll point that out in this molecule. So now we need to count valence electrons. It's 4 for carbon, it's 2 for the 2 hydrogens, plus 6 for the oxygen. We've got a total of 12. So now we need to put in the bonds. So 2, 4, 6. That takes up 6 of the 12. And then we need to make sure that all of the peripheral atoms obey the octet rule. We have 6 electrons left in the 12. They can go around the oxygen to make the oxygen of 8 electrons. And now are we done? Well, not quite. In certain ways, this structure isn't terrible. We're going to cover formal charge today also, and if we looked at the formula for formal charge, you would discover that the oxygen is a formal charge of -1 and the carbon is a charge of +1. So overall, the molecule's neutral. As we knew, I don't see a charge mentioned over here. So that means the overall charge must be 0. So as it goes, this is not the worst possibility. More on that when we get to resonance on I think, Monday. But the next rule says, if you have a situation like this, where there's still an atom that doesn't obey the octet rule, then we will borrow an electron pair, a non-bonding electron pair, in order to make another bond. And so we have a double bond between carbon and oxygen. So that's the structure of formaldehyde. Pure formaldehyde is actually a gas. You're probably familiar with, like, do they still do dissections in biology lab in high school? So you've smelled formaldehyde solution. And we're going to do functional groups next week also. Most aldehydes smell like that. They smell really disagreeable, most of them. One strange exception being benzaldehyde. I don't know why. We'll probably talk about that when we go over functional groups. So there's an example of what can happen when you have an atom that still doesn't obey the octet rule. So you just make multiple bonds. And you keep doing that as many times as necessary until everything obeys the octet rule as appropriate. So again, major exceptions to the octet rule. The one you'll run into by far the most often is hydrogen. Other exceptions to the octet rule can be found in the boron column. So boron and aluminum are also exceptions to the octet rule. They only have 3 bonds or 6 electrons with a formal charge of 0. And those 2 atoms can have 8 electrons around them. It's allowed. But you'll find that when they do, the central atom is a formal charge of -1. So boron and aluminum are never happy. When they have a formal charge of 0, they don't have 8 electrons around them. When they do have 8 electrons around them, the formal charge is -1. So they're never happy. And that has a lot to do with why boron and aluminum behave the way they do chemically. So, but I would be shocked if you run into very many other exceptions besides those. Those, I think, will at least cover the majority of the cases when you run into exceptions. But certainly the other main group elements, carbon, oxygen, nitrogen, obey the octet rule. Let's see. I don't know if you'll run into any cases you might where you have an atom that expands the octet. This might be worth mentioning. If we were to draw the structure of, let us say, sulfuric acid, H2SO4. Sulfuric acid has a hypervalent sulfur atom with 12 electrons around it. And if I'll just save some time and just draw the structure of sulfuric acid for you. I'm not a real big fan of just memorizing structures to memorize them. But if you had to memorize any structure, sulfuric acid isn't a terrible one to memorize. It's pretty common. You learned about it in Gen Chem. It's one of your strong acids, right? It dissociates completely into H plus and HSO4 minus. So that's the structure of sulfuric acid. And if you count them, I think we'll find 12 electrons, 2, 4, 6, 8, 10, 12. Yep. So this is allowed. And I wanted to at least bring up the idea. It's not something you run into a lot. Structures with hypervalent atoms tend to be inorganic. Sulfuric acid is certainly inorganic, right? There's no carbon in it and not a whole lot of hydrogen. But it's something you will run into occasionally, and I figure it's good that I at least mention it. Thing to bear in mind about hypervalent atoms, meaning those that can have more than 8 electrons around them, is you will find those in the 3rd row of the periodic table and below. Those atoms are allowed to have more than 8 electrons around them. They don't have to. They don't have to. You'll find lots of other structures where sulfur has 8 electrons around it and 2 bonds, just like oxygen. That's also totally fine. But the elements in the 3rd row of the periodic table and below are allowed to have more than 8 electrons around them. It does sometimes happen. Even more important, though, if I had all my druthers, if I had my wish, the thing I'd especially like you to remember is kind of the contrapositive or opposite of that, which is the elements in the 2nd row of the periodic table: boron, carbon, nitrogen, oxygen, fluorine. These elements can never, ever, ever have more than 8 electrons around them, ever. There are no exceptions. Those elements can never, ever have more than 8 electrons around them. So if you have a carbon with 5 bonds, it's wrong, without any doubt whatsoever. So you can have hypervalent atoms in the 3rd row of the periodic table and below, but the 1st row, or rather the 2nd row of the periodic table, never, never, ever. Those atoms can never have more than 8 electrons around them. That, I think, is almost more important. If I had to pick one rule for you to remember, it would be that version, that the elements in the 2nd row of the periodic table cannot expand the octet, never, ever. Good, so where are we at? We're at 2:20, we have 20 minutes left, and I want to cover isomers, at least as far as we can. And I guess I've really already talked a little bit about formal charge. I wouldn't mind spending a few more minutes, but I also want to go over some of the different methods of structure drawing, just kind of to get you ready. And again, my goal here, it's not going to be possible for me to do 30 examples of each of these things, but I want to at least lay the groundwork for you guys, so you're ready to go on into the OWL assignments and practice. By the way, I've had some questions, so just to make sure all clear on it, the assignments that are due tonight are also not graded. Those are the introductory assignments. I still recommend you take a look at them, especially the parts on structure drawing, because using the structure drawing tool is not always exceedingly convenient or obvious. So there's a bit of a learning curve on that. But they're not for grading. So which begs the very obvious question, what does it mean for it to be due if they're not graded? I don't really know, because you can always do them later. But anyway, officially they're due tonight. So the first assignments that should be graded should be due a week from today, on the 10th. So there'll always be some assignments that are not graded, and you can always trust that. I've already given you my word. I will never, ever change not graded to graded. But if it doesn't say not graded, then it's graded. So I believe there's 2 assignments. But wait, I lied. I think it's only the chapter 1s that are due next week, right? I'm sorry, I was confusing you with my other class. They have 2 chapters due because they're special. But I think we just have chapter 1 due next week. They might argue with me on that point, but that's a whole other subject. Good, so I think that's all I need to say about that. Any questions so far? I realized I've barely come up for air this entire time. Now that I know I can do a half an hour on electron configurations, geez, I need to watch myself. Okay, well, let's move on then. I want to be sure to say some things about isomers, at least constitutional isomers and structure drawing and all that, and say a few things also about the different styles of structure drawing, just to get you ready for that. And we should be able to do that in 20 minutes. Hopefully I'll even be able to do some examples of formal charge. Good, so let me go back to this molecule. And let's point out a couple things. First of all, actually a couple things off the top. I could just as easily have drawn it like this. We'll even start to worry about condensing structures. That's allowed. You don't have to draw out every single bond. You can if you want to, but we're going to talk pretty soon about condensing structures. And so that sort of thing is perfectly allowed. It's up to your personal preference. But what if I had drawn it like this? Same thing, right? All I did is turned it around. And that's what I mean that you need to develop the ability, even if you're looking at molecules you've never seen before, to tell, are the two molecules the same, or are they what we call constitutional isomers? And the term isomer has to do with two or more molecules that have the same formula, but a different structure. So there's multiple types of isomers. We're going to start here with constitutional isomers, and it's defined in your textbook. But two molecules are called constitutional isomers if they have the same molecular formula, but the atoms are connected differently. These are not constitutional isomers. They're the same molecule. But there is another way to make a molecule that's C2H6O, and that would look like this. That would have the oxygen in the middle. So this molecule will be a constitutional isomer of the other one. So these two are identical. I'll even put same. Why use a long word when a short word will do? But this one is a constitutional isomer of the other one. These are isomers, constitutional isomers, also called structural isomers. By the way, that's something I think is in general true about chemists and seem to be particularly true about organic chemists. I feel like we're never satisfied unless there's two names for the exact same thing, for like every given thing. I don't know why that is. Structural isomers, constitutional isomers, same thing. No meaningful difference between those two terms. So, but I think you can see these atoms are put together differently. There's now two carbon-oxygen bonds instead of just one carbon-oxygen bond. So I would expect you to recognize those two molecules as structural isomers, but those two are just the same molecule drawn two different ways. And we could go on. I've already made the point that you can, that there's almost an infinite variety of different correct ways to draw any given structure. You might have chosen to draw it like this. Same thing. So those two are now the same thing, same molecule, just drawn in a different way. So that's why it takes practice to get to the point where you can recognize that and you don't trip over that. And like I said, I fully recognize it takes practice. As I've said, you're not born knowing this. I wouldn't expect you to come into class necessarily knowing this. You have to practice it. And the reason I'm stressing all this so much is, again, because structure drawing might be the key skill you need to develop for success in this class. As I said, math is not a key skill in this class. There's little to no math in organic chemistry. Mostly we communicate by drawing structures. So that's why I'm stressing it so much. It's because it's just central to success in this class. Good. So as it turns out, those two molecules are the only two constitutional isomers, at least that I could think of. Yeah, I can't think of another one, for C2H6O. Those are the only two ways to put together all of those atoms. Those are the only two possible molecules. And in a couple class days, we'll learn that this molecule is an alcohol and this molecule is an ether when we do our functional groups. There's time for that, though. That will come later. But those are the only two constitutional isomers. And as you can imagine, as you start adding more and more atoms, you get more and more possible constitutional isomers, and it goes vertical almost. I mean, it probably at least exponential, if not more. You start getting, oh, I don't know, 3, 4, 5, 8 carbons. Very quickly, you get into situations where there's thousands or even hundreds of thousands of isomers. It's pretty shocking, actually. But this one's still pretty simple. There's only two possible. So that being said, I think I've probably already convinced you more or less wordlessly that it begins to get a bit tedious to draw out every single atom and every single bond. It's not wrong. You could do this for any structure, draw out all the bonds and all the atoms. It's never wrong. But I think you'll agree with me, before too long, it's getting a little tedious. So that's why I'm also going to clue you into at least 2 ways of abbreviating chemical structures, just to make your lives easier. None of which, by the way, is mandatory. One thing that I've observed every year I've taught organic chemistry is everyone's different. Everyone has different styles in drawing structures. And you should use whichever style works best for you. I personally tend to use a mixture of the other 2 abbreviated styles. And we're going to go over condensed structures today. And I also want to go over line angle drawings. Goes by a couple different names. They're also called skeletal drawings, which sounds bad, but it's not really that bad. Good. So maybe for this molecule here, another way of writing the same thing is CH3, CH2, OH. And again, at least for now, let's put in all of the lone pairs around atoms that have non-bonding lone pairs. Let's at least do that through the first exam, maybe. Maybe then we can start to relax a little bit. But I just want to get us all used to doing that. So that's another way of doing that. And let's get some colors in here. The CH3 refers to this piece. And let's get some blue in. CH2 refers to this piece. Whoops. There you go. So CH3 and CH2 are pretty common abbreviations. And there's endless variations even on those. Maybe you would rather draw the bonds out. CH3 bond, CH2 bond, OH. Fine. Perfectly fine. Nothing wrong with that. You can draw the bonds if you want to. You don't have to, but you can. Maybe we'll give some more examples of some of the larger alkanes. Yeah, I kind of like that idea. Okay, so far though, any questions on that? Oh, yes. No, the question was, are these top 2 isomers? No, they're the same. Those are the same molecule. And the way you know it's the same molecule is all the connections are the same. You've got a carbon bonded to 3 hydrogens and another carbon. That carbon bonded to 2 hydrogens and 1 carbon and 1 oxygen. And we have the same thing here. Carbon bonded to 3 hydrogens and a carbon bonded to 2 hydrogens, a carbon, and an oxygen. Yeah, they have to be connected differently, which we have over here. Here, there's no OH bond. So that has to be isomers. So it's a good question. That's how you know if you're dealing with identical molecules or isomers. If all the connections are the same, then the molecules are the same. Yes? An ether. Yeah, we'll get to that. Mm-hmm. That's a good question. I don't think there's a rule there. Isomers can have the same functional group or different functional groups. Yeah, I don't think there's any rule there. Interesting question. We'll find out more about that too when we start talking about functional groups. But in general, I can't come up with a rule. I don't think there is one. Other questions? I feel so bad for the people behind me, staring at my bald head all the time. Okay. So where were we? Oh, we're condensing structures. Yes. Now then, maybe we'll move over to the alkanes just because, and we'll learn what alkanes are pretty soon. We have a whole chapter on alkanes. But the simplest alkane would be methane, CH4. We'll go over what these things are named also. That's, I think, in chapter 2. So there's only one way to connect a carbon and 4 hydrogens. That's unambiguous. Likewise with ethane, CH3CH3, C2H6, there's only one way to connect 2 carbons and 6 hydrogens. And I believe you'll find the same thing for propane, CH3CH2CH3. Yes, that's the same propane that's in propane and propane accessories, same molecule. And I think you'll find there's only one way to connect all those atoms. But once you get to C4H10, now we have some different possibilities. So this is one of them. And we're not doing it in chapter 1, but pretty soon we'll do nomenclature and we'll learn that molecule is called butane. You might have heard of butane. It's used in cigarette lighters. It's that clear liquid inside. And so that's one way that you can put all those atoms together. Another way looks like this. And those are the only two possibilities. And I think already you're seeing how useful it can be to condense structures. It's just a lot less work. Now, that being said, if you wanted to CCHHCH, if you wanted to do it that way, I can't stress enough, that's not wrong. You can feel free to do that. I just think at some point, do you want to call it 4 carbons? Do you want to call it 6 carbons? I don't know where you want to draw the line. We might all draw the line in a different place. But at some point, it's beginning to get a bit tedious. I think you'll agree with me. And so it becomes useful to be able to condense structures like this. Like I said, if you wanted to draw the bonds in between the carbons, that's fine. You can most certainly do that. It's optional, whichever you prefer. Both are completely fine. But we can abbreviate even beyond this into what we call line angle drawings. And so that would be a way of drawing butane also. And the way that there's these dots around, let me erase them, it's getting confusing. There we go, that's better. So the way and that's not the only correct way to do it. I could just as easily have gone like this, let's say, same information. I could even have gone like this, same. But the way line angle drawings work is that every line between 2 points like that, assuming there's no other atoms besides carbon and hydrogen, is going to be a carbon-carbon bond. And so every point or sharp corner is going to be a carbon atom. And so we count 4 carbon atoms, 1, 2, 3, 4. And all of the valences that are not shown are assumed to be hydrogens. So for instance, coming off of this point over here, I see one line coming off. That's a carbon-carbon bond. But carbon is 4 bonds with a formal charge of 0, which we can certainly expect here. So that means there's 3 bonds here that are not shown, and they're all to hydrogens. That's why it's CH3. Likewise, this corner over here, that has to be a CH2, because there's 2 carbon-carbon bonds that are shown here. So there's 2 bonds that are not being shown, and those are to hydrogens. Now, I should even tell you, you can show the hydrogens if you want to. It's not wrong. You can do that if you want to. It's just not necessary. And there's no reason you really should unless you're trying to point out something about those hydrogens, let's say. So that's another way of abbreviating structures. I tend to use a mix of condensed and line angle drawings when I draw structures. But you should experiment, figure out what works best for you. Because again, even though I'm not directly grading your structure drawing in exams, you'll need to be able to draw structures to do well in these exams. Yes? CH5 would not be a neutral compound. Well, CH5 is impossible because carbon can't have 5 bonds. Now, do you mean like C2H5? C2H5 is also not going to be a neutral compound. You mean this one, C2H6? Oh, you're saying how would you do that with line angle drawings? It's a little silly, but you would just draw a line. I'm not saying you're silly. I'm saying doing this is silly. But it's not wrong. Yeah, you can do that if you want. Yeah, absolutely. It's not wrong. I don't know about methane. Do you draw a dot? I guess. I've never seen it done. Again, it's a good question. There's nothing wrong with your question. I'm just saying at some point, it gets a little silly in the opposite direction. You mean something with like a charge on it. What about Well, let's do one. Let's do C2H5O minus. Is this kind of what you mean? Yeah, okay, well, let's do it. I'll skip the parts with counting valence electrons. I'll just draw the structure. I think you'll find once you've added in all the electrons, you'll get something like this. And if you use that formula for formal charge, you'll find the oxygen is a formal charge of -1. So that's where the minus charge comes from. Also, when we get to acid, you touched on several things at once. We'll learn that this is called the conjugate base of this guy. That comes later. We'll get there. But be that as it may, so that's how you would draw that. Now you're saying how you would do that with a line angle drawing. You could go like this. Perfectly fine. Either way, or you could go CH3, CH2, O minus. Fine also. Any of the above are fine. I consider them all equally correct. They all show the same information. No one of those is any better or more correct than the other. They're all fine. Yeah, you would want to, so actually and it's fine that you are, that's one step ahead. I was hoping at least to say some things about formal charges, or here's another way to handle it. Thank you for the segue into formal charges. Here's an example of a species with formal charge. So yes, you want to put the charge on, you want to mark any non-zero formal charges. And you do it just like that. I'll do one with a plus charge also, so you can see what that looks like. Yep. Before we do that, any other questions? So like I said, it's okay if you don't have this whole business worked out yet. You need to practice and you need to get in there and see what works for you. My guess is most of you will start at least condensing structures with a lot of hydrogens. It just gets a little tedious. But again, no judgment if you do want to draw out all the bonds and all the atoms. It's not wrong. It's perfectly acceptable. It's just a matter of what you want to spend time doing. So since we've gotten into an example of a species with a formal charge, I think you'll find this is the only way to put together C2H5O minus and put the minus charge in oxygen, which is the most electronegative atom. It'd be a little weird to put the minus charge in carbon, since carbon isn't very electronegative. So these are all correct ways of drawing. Again, of course, I could have put the oxygen in any one of those 6 positions. It's the same thing. Not only would I not take off points, I wouldn't even notice. It's just different ways of drawing the same thing. But so as I said, I have a formula in your class notes that you can use to calculate formal charges. You're probably familiar with it from Gen Chem. I bet though, if once you've practiced a while, you won't need to use that formula anymore. You'll just say, oh, I've got an oxygen with 1 bond and 3 lone pairs. It must have a formal charge of -1. After a while, you'll just recognize that. And not only that, I've left you tables of common atoms with +1 and -1 formal charges. So you have that as well. But since we're going into, I want to do just one more structure since we're going into resonance next. So just as another example of abbreviating structures, let's consider benzene. And also allows me to point out that compounds can be cyclic. You can have rings of carbon atoms. So this molecule here is called benzene, and you might have heard of it. That's a perfectly acceptable way of writing it. If I were to draw that using a line angle drawing, and I think you'll see it really saves time. So once again, all of these 6 bonds that we're not showing are assumed to be to hydrogen. And I bring up benzene because we're going to go into resonance, I think, on Monday. And with that, I'm actually out of time. So hopefully that at least gets you started on structure drawing. Best piece of advice I can give you over the weekend, get in there and draw. Draw structures, draw, draw, draw. I promise you it will not be wasted time. Other than that, have a great weekend. We'll see you Monday.